Hi students, in this video we are going to see about a delay flip-flop. Delay flip-flop is just a simple modification of your SR flip-flop. What is the disadvantage of SR flip-flop? We will be having indeterminate state. Why that indeterminate state is coming? Because the input is having 1 and 1 and output is also having 1 and 1 at the logic 1 and 1. So to avoid this indeterminate state, input should be complement with respect to each other. So what we are going to do with the SR flip-flop is we are going to do a slight structural modification in the SR flip-flop such that R will be the complement of S. So we are connecting an AND gate here in such a way that this 1 and 1 combination won't appear in the input as like your SR flip-flop to avoid your indeterminate state. Okay. So again the same circuit diagram only. I am going to give this clock, and again this is going to be this Q and Q bar. Okay, and now what I am going to do, I am going to tie this with the help of a NOT gate by using an AND. Okay, so this common input is said to be D, but here this is S and this is R. Am I right? So this is how you will be drawing. So now how will you go ahead with your truth table? You have your present state, you have your D input. So keep in mind D input is nothing but yes. D input is nothing but your yes. Okay. And you have your Q plus and Q bar plus. And now we have tied together, and we have only one input here D and one more, that is your present state. So 0 0 0 1 1 0 1 1 will be the input combination. Again you are considering this as a positive clock pulse. Okay, level triggered clock pulse. So when S is 0, what will be your other one? R will be 1, right? S is 0, R is 1. As I already said, S is 0, R is 1. Come here, S is 0, R is 1. That is said to be your reset state. This is said to be your reset state. In reset state, what you will have? You will be having 0 as the output. See, look ahead. S is 0, R is 1. You will be having 0 at the output. Okay, you will be having 0 at the output. Let me fill this table out. If this is 0, this is 1. So now this is 1. And now S is 1 now. R will be 0. What is said to be 1 0 combination? 1 0 combination. 1 0 combination, that is said to be set state. Am I right? This state goes here. 1 0 combination is set state because you have 1 at the output. So what I will do? I will be writing 1 here. I am having 1, I will be having 0. And again, this is also again same. If this is 0, this is 1. So when you have the 0 1 combination, this is said to be reset state, and when you have 1 0 combination, I will have set state. The other combination is 0 0. Okay. So this is for your understanding I have drawn. This is the truth table. Okay. This is your truth table. So look with your D. Whatever input D and Q, compare your D and Q plus your next state output. Whatever you have in your D, that is occurring in your next state. D 1, this is also 1. This is 0, this is 0. This is 1, this is 1. Okay. So the same input, same output you have as like your input. Hence, this flip-flop is otherwise said to be delay flip-flop. Okay, whenever you want to produce some delay in digital circuit, you can use your delay in giving the input in digital circuits. Then you can have your D flip-flop. Okay. So, how will you draw your excitation table? Excitation table is between your present state and your next state with respect to your input. Okay. So, now Q plus D. So, 0, 0, 0, 1, 1, 0, 1, 1. As I said already, output and input are same. So, the same thing will appear at the output also. So, 0, 1, 0, 1. Even you can even compare and write as like your SR flip-flop. Okay. This is about your excitation table of D flip-flop. Okay. So, let me come ahead with the JK flip-flop. Again, JK flip-flop, what we are going to do is, here also we are going to avoid the indeterminate state. Okay. To avoid the indeterminate state. But we will have two inputs here. Okay. We will modify that indeterminate state by the structure of JK flip-flop. Avoid this by modifying the structure of your SR flip-flop. So, what is that structure? Okay. So, again the basic SR flip-flop is same here. You have a clock, you have a J input, you have a K input, and then 1, 2, 3, 4. This is Q, this is Q plus. See here, output Q will be connected as an input to the second flip-flop. And similarly, this output Q bar will be connected as an input, third input to your first NAND gate. This is the structure of your flip-flop. This is the structure of your flip-flop. JK flip-flop. Okay. In JK flip-flop, so if you know your SR flip-flop, everything is common. Okay. So we have your present state, truth table I am drawing, J and K as like your S and R, Q plus, Q bar plus. So this you know, this is your present state, this is your next state. See here we bother about only the indeterminate state. Indeterminate state will occur for one input combination. The rest all is same as like your SR flip-flop. The rest all next states are same as like your SR flip-flop. Okay. 0, 1, 0, 1, 1, 0. Okay. I am not going to derive. You can try by yourself. 1, 0. Okay. This state alone we need to check. So 0 and 0, and your present state input is 0. Okay. Your input is J is 0, K is 0, clock is always 1. This is your clock. And the present state input is 0. So Q is 0. Okay. So when these two are 0, 0, first these two are 0, 0, this is going to be 1, definitely this is going to be 1. And then when this is 1 and 1, one of the input is 1 and 1, the output will depend on the previous state. So previous state is 0. So this Q goes here, this is 0, so this will be 1, and if this is 1, 1 and 1, this is 0. See here we have 0 here and 1 over here. So whenever you have a combination of 1 and 1 or 0 and 0, I am getting 0 and 1. Okay. When I am having the input combination 0 and 0, I am having 0 and 1. This is verified. This is validated now. Okay. I have to go ahead with 1 and 1 combination. 1 and 1 combination with the previous state to be 0. Okay. So this is 1, this is 1. Okay. and see, this is 1, this is 1, this is 1, and my previous state is 0. Since my input is all 1 I am having, I need to proceed only if I know the previous state. So this Q is 0, and that is tied up to the second gate. So this is 0. So this is 0, this is 1, this is 1. So this will be 0. 1, 1, 0. Okay. 1, 1, 0. And definitely if Q is 0, this Q bar, this is being connected, this will be 1. 1, 1, 1, this is, when any one of the input is 0, this is 1. I'm sorry, I made a mistake here. So this is 1, 1, 1, 0. This is 1, 1, 0, that is 1. So when this is 0, this is going to be 1, and this is 1, okay, and this is carried forward, and this is 1, this is 1, this is going to be 0, this is 1, 0. Output is 1, 0. So when I am having 1 and 1 with the previous value as 0, I will be getting 1, 0. Okay. Again, I have to go ahead with Q to be 1. Previous state, if this is 1, if this is 1, what is going to be your output? So when the previous state, now again J and K is 1, the clock is 1. So the output of 1 and 2 depends on the previous state. This Q is connected here, this is 1. So 1, 1, 1, when all are 1, your output of the NAND gate is 0. And if this is 1, the previous complement Q bar is also 0. So that is connected here, this is 0, this is 1. When this is 0, output of 4 will be 1, and this 1 will be carried forward, 1 and 1, this is 0. Okay. Now for 1 and 1, when the previous combination is, previous state combination is 1, your output is 0 and 1. Okay. So as like your SR flip-flop, this is said to be no change state when your input is 0, 0. This is said to be no change state. This is said to be reset state. 0, 1 combination is said to be reset state, and 1, 0 combination is said to be set state. 1, 0 combination is said to be set state. Now compare your 1 and 1 combination. When this is 0, this is 1. When this is 1, this is 0. Okay. When this is 1, 0, this is 1, and this is 1, this is 0. Compare your present state and the next state. This state is said to be toggle state. This state is said to be toggle state. You have a toggle between states. Toggling means 0 means 1, 1 means 0. Okay, this is said to be toggle state. Okay. See, focus on your SR flip-flop. If you are familiar with your SR flip-flop, all the other flip-flop will be easy. So excitation table, let me go ahead with the excitation table. So Q plus excitation table is between the present state, next state, and your inputs JK. So 0, 0, 0, 1, 1, 0, 1, 1. Okay, let me go ahead. 0, 0 will be there. Okay. 0 and 0 of your input will be there in 0, and 0 of your present state will be there in your 1 and 2. Okay. So for 1 and 2, J is 0, 0, and K takes the value of don't K state. Okay. So 0 and X. And then for 0 and 1 combination, okay, for 0 and 1 combination, this is in third and fourth stage. This takes the value of 1, J takes the value of 1, K takes the value of 0, 1. So that is 1x. Okay. And then 1, 0 combination, 1, 0 combination between your 6th state, 4, 5, 6. 1, 0 combination, 6 and 8, 1, 0. So see here, K is 1, whereas J is don't care. K is 1, J is don't care. The next one is 1 and 1 combination. 1 and 1 combination is there in your this state and this state, which is number 5 and 7. So here you have K0 and J takes the value of don't care, X and 0. This is about your JK flip-flop. This is about your JK flip-flop. And then come to your T flip-flop, otherwise said to be toggle flip-flop. In your toggle flip-flop, tie your J and K together. Tie your J and K together. The diagram is same as like your J flip-flop. Toggle flip-flop, J and K will be tied together and it is named as T. It is named as T. Okay. So again, so we have how many combinations here? We have Q and T, Q plus and Q bar plus. And this is input combination 0, 0, 0, 1, 1, 0 and 1, 1. Let me go ahead with 0, 0. So when your input is 0, this both the inputs are 0 and 0. Okay, J and K. Earlier it is J and K. So both are 0, 0 means output is 1 and 1. When both are 1 and 1 means the output of the flip-flop depends on the previous state output. So this is your previous state 0. So this 0 goes here. 0 and 1, 1 and 1 and 1, 0. So Q is 0 and Q bar plus is 1. And then go ahead with 1 and 1. So when you have 1, so you have 1 and 1 here. So now this is 1, the clock is 1 and you are solely dependent on the previous state. The previous state is 0 again. So this 0 will come here. So this will be 1. So if this is 0, this is 1 and all are 1, this is 0. And if this is 0, this is 1. And this is 1, 1 and 1, your output is 0. So 1 and 0. 1 and 0. Okay. And again now your Q is 1. Now Q is equal to 1. So for Q is equal to 1, let me take toggle input 1 as 1 itself. Okay. So this is 1, this is 1. So I solely depend on the previous input. So 1, 1, 1, this is 0. And this one is 0. And if this is 1, this is 0, right? So this is 1. And if this is 0, this is 1. And if this is 1, this will be 0. So now this is 0 and 1. So I am taking for T1 and Q1. Okay. So this is 0, 1, 1 again. And next one is for 1, 0 combination. You will be getting 1, 0 only. You can check. Okay. And your excitation table. So Q plus 0, 0, 0, 1, 1, 0, 1, 1. Okay. So T flip-flop, I will be getting, if 0 and 0, I have only one combination of 0 and 0, that is 1. For 0 and 0, your T is 0. And then for 0 and 1, your T is 1. 0 and 1, T is 1. And 1 and 0, T is 1. Okay. So for both the cases, 1, 1. And for 1 and 1, your T is 0. So this is about the excitation table of your T flip-flop. Okay. With this I will complete this flip flop. Thank you.